Yes, audible and good evening, sir. Yeah, I'm good, thanks, sir. Good. Okay, sir. Okay, sir. Sure, sir. Sure, sir. Sure, sir. Okay, sir. Yes. Yeah. Yes. Yes. Sir. Yeah. Yeah, sure, sir. Shall I start the presentation or I'll just introduce? Yes, sir. I prepared presentation. So is my screen visible? Uh, is my screen visible? Sure, sure, sir. Uh, so, sir, is my slide visible to you? Yeah. So I'm Abhinav Thakur, final year BTech student in the department. Mm, I think there is an issue. Uh, a final year BTech student in the Department of Electrical and Electronics Engineering at NIT Delhi. I'm also pursuing my degree in System on Chip Design and Internet of Things. Uh, my area of interests include semiconductor devices, silicon photonics, and quantum technologies. Uh, and my tools which I've used, which are relevant for this internship, are COMSOL Multiphysics, MATLAB, and a Circ language, which is for quantum computing. Certification are uh, India's Semiconductor Workforce Development Program by IIC Bangalore and Synopsys, in which I got exposure to TCAD. I've also done an Introduction to Quantum Computing course by the Coding School, and I'm currently doing a hardware of a quantum computing course, which is organized by DevTex on edX platform, which is ongoing. And I did a very short course on VLSI fundamentals at NILET Calicut. So this was a project which I did uh, at research internship last summer at National Chungcheong University, Taiwan, under the guidance of Professor Guan Chang. It is a simulation of germanium-based single photon avalanche detector. So we have this structure which has P plus germanium tin, and then intrinsic germanium tin, and silicon for absorption of the material, absorption of the, sorry, for avalanche triggering of them. For this is for the multiplication region, and germanium tin is for the absorption, and this is for N plus silicon for contact. And simulation technique which I used is I took a very infinitesimal uh, section of the device and used periodic boundary condition so that I could get the result for the complete device. So this is, if you can consider this block as a very small part here, and I've used a periodic boundary condition. So I mean, we get a the simulator considered it as a lot of uh, various devices, various sections. So this is a very small section which I have taken it from here. I mean, it could be considered. So this is the uh, electric field distribution. These two are the electric field distribution we got uh, by simulating the device. So we can see that here most of the light is here light is getting absorbed, and we get a bit of uh, oscillations in here. So we also see the absorption and total reflectance of the complete device as we vary the reverse bias here. So under the unbiased condition, we get a 40% of absorption and 32.7% of total reflection for your devices. So we can also see that we get electric field due to charge carriers in the silicon region. So we can see a very high electric field is being developed in the silicon region, which is due to avalanche uh, triggering uh, because for single photon absorb detection, we need a because of we get a very for example a single photon, so we need to amplify the electric field so that we could detect that we have received a single photon. So we need a very high electric field. So we need avalanche triggering of electric field. So this structure is good for single photon detection. And same we can see this heat map, which is also for uh, single photon. I mean, which is also for intrinsic silicon region. We can see a high electric field being developed due to a avalanche triggering, and because a lot of charge carriage has been generated in the silicon region. This is the semester project which I did in the seventh semester at my university. So for this also I used germanium 10, 10%, which has 10% germanium 10 in it, based PIN flow detector. So it has this structure, PIN structure. P plus I have used germanium, intrinsic germanium, then germanium buffer I've used because of the lattice mismatch, and because of strain difference between the lattice of germanium tin and silicon. So it could cause distortion in the uh, uh, structure. So that why buffer is used, and I have used buried silicon so that light can be confined in the device and can be absorbed completely. And then we have got a silicon substrate, and below it I have a gold reflector so that whatever light is remaining, it could be reflected back into the device so that we could get a maximum absorption from it. So here we can see that most of the light is getting confined. I think we are getting a I think uh, 0% light is getting reflected. I think the data is in the next slide. You can see that again oscillations are here, and most of it in the this region, buffer region and intrinsic germanium region. Sorry. So we are getting absorptance of 81% and reflectance of 19%, and no light is getting transmitted through it. And this is the current versus voltage. So as the reverse voltage increases, we get a high current, and um, then it gets saturated at a certain point. So which is a characteristic for PIN photodetectors. A characteristic, characteristic graph. As same is for responsivity. I got a good responsivity of 0.4585 ampere per watt at minus 1 volt. Uh, so this is the uh, project at which I did. This is to demonstrate a BB84 quantum key distribution protocol. I did this as a capstone project when I did my introduction to quantum computing course, online course, which was conducted by Coding School. So we can consider that uh, uh, polarization of light, which is continuously changing. So we are, we are considering the vertical as one and horizontal as zero, and it is and polarization we can consider is in the superposition of zeros and ones. Uh, so when we measure it in the rectilinear basis, which can be for forward zero, we are considering horizontal, and For vertical, we are considering 1. So when we measure it, then the superposition gets collapsed to either 0 or 1. And when it same happens for diagonal basis, but for diagonal basis, for example, we are for if it get collapsed in a forward slash kind of fashion, then we are considering it as 0, and for backward slash kind of fashion, then we are considering it as 1. So for this protocol, I mean, protocol, we have two, for example, Alice and Bob. And uh, for example, if from here Alice uh, projects a photon, then it could in the diagonal basis, and Bob is measuring in the rectilinear basis, then it could collapse. It has 50% chances of getting collapse in 0 and 50% chances of getting collapse in 1. So we can see that if uh, what Alice does is it selects its basis. For example, uh, it could randomly select a basis. For example, this one is diagonal, this was in rectilinear, then diagonal. Alice randomly selects its basis in which it wants to uh, project its photon, and Bob also randomly selects its basis. So for example, Alice selected basis, and then it for diagonal basis it projects electron in one kind of fashion, and for rectilinear it projects it in 0 kind of fashion, and thereafter all these electrons selected, then Bob measures it. If the bases are same, then I mean they will get the same result. For example, if Alice projects in 0, then Bob also gets 0, because both of bases are same. But if bases are different, for and yes, sir. Okay. So am I audible? Was I audible? Yeah. Okay. So similarly, and if both of them do not get the same result, they will basically then match their bases. If their bases are similar or not over a not a quantum, because these are done on over a quantum channel, because in quantum computing, quantum channel is used for quantum entanglement part, and uh, quantum superposition. So it is quantum properties of the material are exploited, or light are exploited. So, but they need to know that if their message is correct, so they will reveal their basis over the classical channel, class channel that whatever communication channel we are using now. So they will reveal their basis. If their bases are not same, then they will just discard whatever data they have uh, for it, and the remaining uh, for example, 100, they will use it for establishing communication channel between them, because this is their communication key. This will be their communication key. 100 will be their communication key, and this will be used to secure the channel and establishing the secure communication channel. And they will know that uh, there is no eavesdropper, or they are not being spied, which I've demonstrated here, that if there is a eavesdropper which detects a photon, for example, it uses a rectilinear basis, then it might get 1, and then it will project 1 to the Bob, but he may get 0. Then they will know that they have not uh, uh, someone has spied, and they will reestablish the whole process. And similarly, they will not be spied upon. So this is the my results which I have got when which I uh, using when I programmed it, when I simulated it. Uh, this is the I just used to demonstrate it. Similarly, I've this is for Alice bases are CHH. It is similar to previous one. Then if there, for example, Alice bits are 100, 101, 111, and 00, and then uh, I'll- and they match the bits. Uh, they match the bases. See, these are the Alice bases and these are the Bob's bases. Whichever uh, bases are being matched, then uh, they use that for establishing key. And if eavesdropper is there, then they understand that for her they get the expected key as 010010, but actual key was 11001 according to Alice Betts. So that's why they understood that there is eavesdropper here. This is the dynamic charging of electric vehicle project that I did in summer internship in 2023, uh, which is basically, shall I sir explain it or leave it for dynamic charging? Uh, so I'll just briefly explain it. So dynamic charging of electric vehicle, what we tried at, our vehicles get charged while it is moving. So we have two coils present on the road and in the vehicle. So when a car moves due to electromagnetic induction, our uh, we get the electromagnetic induction, we get the charging of the electric vehicle. So we have a grid, then we convert our AC to DC, and then convert DC energy, DC signal into high frequency EC. Then we have a compensation network. Then our energy gets transmitted. Then we have again compensation network on the vehicle side. Then AC is converted to AC and it is used to charge it. This is the circuit we did, and these are the results of charging. So yeah, that's all. Thank you. Yes. Well, I used I should stop there. Software I used, it was the Circ language is there, CIRQ Circ language is there. I used Circ language for it, and it was done on Google Colab. Both I've both I've used console. I've used console. System on System on chip design. I learned about digital IC design, and rest are IoT. The rest courses were for IoT. Also, I have used Tanner EDA tool for circuit simulation for it. For example, SEdit, EEdit. Rest core there are we for the SOC design and IoT course we had to do four courses. So one course was for digital IC, rest were for signal processing courses, kind of. Uh, uh, so uh, so on future, I want to go for masters in the silicon photonics field, and I want to work for in the area of silicon photonics based quantum computers. So I think this will help me a lot to gain deeper insights into the photonic devices, which will help me to get into my desired area. Yeah, yeah. Uh, I'm definitely outside of India, and I'm also considering. I mean, Taiwan, definitely National Taiwan University is because I'm getting an internship here. So I'll keep it in my list as a very high priority because it is also very high ranked and highly reputed institute internationally. So yeah, I'll be applying for in 2026, but for application I'll be applying for various places and I'll be keeping NTU. Yeah, yeah, I visited it. I visited. Yeah, yeah, I visited the lab website. Yes, sir. Yes, sir. Your screen visible. Yes, sir. I visited it. I got the professor. I have got the professor's contact from here itself. Yeah. Mm, 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 mm. No, I do not have experience about fabrication work, but I was introduced to it in the ISWDP course about theoretical part of it. Some of the through the S process tool of TCAD. I mean, it simulates fabrication process itself. Yeah, S process. Mm. No, no, not that. It is S process for TCAD Centerus. It is yes, yes, it is Centerus. Centerus. Oh, mm, okay. Yeah, yes, sir. Mm, 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 mm. Yes. Mm. Oh, for VACL. Oh, uh, yes, sir. Yeah, 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 yeah. Yeah. Mm. Oh, yeah, yes, yeah, yeah, yeah. Mine was group 4 based. This one I think 3 5 based SPOD. Oh, nice. Yeah. Mm. Sure. Sir. Mhm. Yeah, yeah. Mm, mhm. Yeah, yeah, yeah. Sure. Yes, sir. Mhm. Yes, sir. Uh, what's the question? I did not. Yes, sir. So, I mean, do I have a project in my mind? Uh, Mostly, I want a project which is under. I mean, for example, that was a good project, SPAD, because I already had an experience on it. But mostly, I want. I mean, I wanted a, experimental outlook to it. I wanted to do experimental project, but I mean, simulation part is also. But I would like to get a uh, experience in experimental part also, apart from simulation part. Yeah. Yes, sir. Okay. Understood. Yes, sir. Yes, sir. Yes, sir. Yeah. 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 Okay. Okay. Yeah. Yeah. Oh, understood, sir. Yes, last time I came to Taiwan for, yeah, yeah, for only Taiwan. Adapted to it. Yeah, I was pretty flexible because food was not a big issue for me. Yeah, language was a bit of issue, but I managed through, I mean, Google Translate, and I also tried to learn. I also tried to learn a bit of Chinese. We had a Chinese course at CCU, so yeah. No, mostly I think we have discussed most of the things on call also about the logistics and all. Uh, we have discussed it out. I, uh, I mean, just by when can I get a project? I mean, yes, 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 sir. Audible. But I'm getting a white screen. Yeah, screen is white. Yeah, is visible. Yes, sir. You're audible, sir. No, sir. It's a white screen. Yes, sir. Mhm. No, sir. I think you could share entire screen. I think you're just presenting a window. That's yes, sir. It is visible. Yes. Yeah. Okay. Yeah. Yeah. Yes. Yeah. You are not audible for. You are not audible for or are not audible from the previous slide. Uh, yeah, okay. So yes. Yes. Yeah. 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 Yes. Yeah. Yeah. Mhm. Yes. Yes. Mm. Yes. Mm. Yes. Yeah. Mm. Yes. Mm. Yes, you told. Yes, yes, you told me about it. Yeah. Okay, okay. Yeah. Mm, 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 mm. Yeah, well, yes, sir, obviously. Yeah. Mhm. Nice. Mm, okay. Oh, okay. Sure, sir. Yeah. Mm, yeah, sure. Yeah. Okay, sir. Mm, mm, mm. Sure, sir. Yeah, sure, sir. I mean, by when can I get confirmation? Yeah, yeah. Sure, sir. Yes. Sir, you are not audible. Now. Oh, okay, okay. Sure, sure, sir. Thank you. Thank you. Thanks.